So yeah, welcome again, everybody, for our third CMFI mass spec seminar series. So we're moving on from like fundamentals to now some, well, still fundamentals, but already like a little bit more advanced stuff. And then also, hopefully, we want to do like some first hands-on examples today. So I think the idea in the longer run is to like present different like software tools, how to analyze your data, and then we're slowly getting into that now. So yeah, today we're going to speak about liquid chromatography and how to couple this to mass spectrometry, and then about tandem mass spectrometry. And that will also be like the very fundamental basics for molecular networking, which I want to introduce briefly. And then next week, we're going to talk a little bit more about how to acquire data and how to convert this to like open access formats. And then, yeah, if everything goes as planned, Peter will present on molecular networking then after that. And then we will also dive into feature finding with different tools. Efi volunteered to present us OpenMS, which I'm going to be super excited about. And then, yeah, maybe Tomasz and Robin from MZMind will give some guest lectures. And then, I don't know, I think this will become a little bit more dynamic. So very much looking forward to that. But yeah, first today, yeah, HPLC-MS and tandem mass spectrometry. And yeah, again, some fundamental information here. So in case you did not sign up, there is a link you can sign up, and here also like find under that other URL like the document with like the general description of our course. There's also a link to like YouTube where I intend to like upload all those sessions. So if you miss one, you can watch it later on YouTube, or I don't know if you want to revisit some like particular parts. All right. Then, yeah, as I said, today we're gonna check out how liquid chromatography can be coupled to MS, and then how we can use this to acquire MS data. And maybe to start with a little recap, who wants to tell me like what's like the most essential thing we mentioned during the last two sessions? So there's really this is like super important later on. Mass spectrometry displays what? Somebody wants to say it? No? Axel, come on, I see you here on the top. It does display
mass overcharge.
Thank you. Yeah, this is really important. So we just had this discussion in the lab the other day about doubly charged ions, and sometimes there comes confusion. So really like keep this in mind. Then, yeah, in addition to those fundamentals, we presented like ionization methods, such as like ESI here, and different mass analyzers, such as the Orbitrap. And like that combination of the two, ESI and a mass analyzer, is already like the perfect setup to couple that whole thing to liquid chromatography, because that's what most often used. Like ESI, electrospray ionization, is like perfect, well, not a perfect, a very well-suited interface to couple like this.
Brace yourselves, gentlemen.
Yeah,
according to the
chromatography is so important
the
that it even
secret
made it to the
ingredient is love. Who's been screwing with this thing?
So yeah, I think we had to comment before that we should like maybe talk a little bit about fundamentals there too, and I just like prepared like a couple of slides to introduce you to chromatography really quick before we move on to hyphenating this to mass spectrometry. Yeah, here in this like nice animation, you can see basically the idea is that we separate compounds over like a column, could be like an HPLC column, before we then move it on to like the mass spec and then get like a mass readout. And yeah, just like a little bit about history. So chromatography is I think a very old, long established like analytical method, and it all started with like this like paper chromatography, which you may have seen in like one of like the practical courses you attended, where you can like very nicely separate like here different pigments in like, yeah, like a paper matrix with like some like solvent as a mobile phase. And in a sense that yeah, kind of like happens over time, obviously, as like the paper sucks in like the liquid. right? And now you have basically an interaction between like the different like pigments and the mobile phase, so like the solvent that gets sucked up here from the bottom, and the stationary phase, which in this case is like the paper. And from a chemical perspective or physical chemistry perspective, this is kind of like an extraction, what's going on there, right? So like you may have seen like these liquid-liquid extractions where you have like two different liquids that are not mixable. And then you have like some molecules in there, and then depending on their polarity, they either go in one phase or the other phase. And if you understand that's, I think, pretty much what also is happening here in like a chromatography separation. So now the only difference is that in this case with the paper, or also with like HPLC or so, like one of the phases is actually solid and the other one is liquid, right? So like your paper is solid, and then the mobile phase that runs through is liquid. And what you have is a kind of like distribution between like, basically solubility or like absorption of the molecules you want to separate between like that mobile phase and the stationary phase. And then, you can basically see how, depending on this equilibrium, how different molecules dissolve and resolve between like the two phases at like a different like constant. And hence, like they, for example, in this paper chromatography, they move differently, like fast, or in a column chromatography where it's pretty much like the same principle, right? You would also just like elute them at like a different time than out of the column. And this is exactly the principle of like UHPLC or HPLC, for example. And now we can like have different columns. So you can buy, for example, like a classic silica column and separate stuff based on like polar interaction, or helic, that would be for polar interaction. Then reversed phase, which is probably one of the most commonly used stationary phases for non-polar interactions. Then there's also like ion binding, so basically on ion exchange columns, or boiling point for like gas chromatography, where, well, actually one phase would now not be like liquid, but like actually like a gas. And then size exclusion, or also affinity, for example, in like protein purification techniques, such as like nickel affinity chromatography. All right. That being said, so here we have an example of like a reversed phase chromatography separation, and you can see here on the bottom, like there is like this different. In our case here, it's like only like a C5 chain, and you can see that like the molecules above in the mobile phase kind of like bind either like more often to like that stationary phase and hence move slower through it, or like here that other molecule, which you may see has a hydroxy group, so that's more like non-polar, hence it does not interact as closely as here that other like alkene with my stationary phase, and hence has like a shorter retention time, right? Because it elutes earlier from the column. And so okay, this example here is C5. I don't know if that's actually commonly used, it's just an example, but what we typically have is like C18 chains or C8, then some phenyl end groups for like pi-pi stacking. And then there's all sorts of like, different variants with like polar shields in the middle and different end capping of your silica beads. So it's really like a huge scientific field, separation science, and pretty exciting. So I think for many mass spectrometrists, this is mainly a way how to bring in your samples into the mass spec, but having good chromatography is really essential if you want to like do like nice LC-MS data acquisition, because like the better your separation is, the better your eventually signal to noise is, and the cleaner your mass spectra, which has in particular implications for tandem mass spectrometry. All right, so talking about peaks a little bit. So a peak is basically here like the signal intensity of a molecule that like elutes at a certain time, and it's kind of like the same thing as a band here in thin layer chromatography, for example, just that you have like this intensity dimension. All right, so like here, if we would plot this, we get like here an intensity over the time or volume of my separation, and then hopefully you get like a very nice Gaussian distribution here in a nice chromatographic separation. Then from there you can like calculate different values like the retention factor, selectivity, or chromatographic resolution, which basically tells you how well your separation might be and how good your retention to the chosen stationary phases. So now for us, what is I think really important is that we kind of like have like this even like distributions, ideally Gaussian, and then also that this resolution here is like possibly high, right? And what that basically results in is into something which I think we commonly call a nice chromatogram, right? And oftentimes we unfortunately see not so nice chromatograms, but just to give you like an example, this here is like a 5 component QC mix we typically run from like different sulfonamide antibiotics, and you can see very nicely that those peaks are like very sharp, right? So those are like here, very narrow, almost looks like GC peaks. So this is very high resolution for like a UHPLC separation. They're kind of like Gaussian, but you see many of them have like this little tail, but that's all like within an acceptable range. So if I would look at your paper and you have a chromatogram like this, then me as an analytical chemist, I would say, okay, that's a nice peak shape, and it's probably you did some good work there. And this becomes really important when you then like look at like the masses that are like behind these peaks, and especially if you look at like the MS spectra, because like obviously like the more thin that peak is, the higher it actually like pushes, right? And hence the better your signal response will be. And I think in non-targeted metabolomics, where we have potentially 1,000 or tens of thousands of different molecules, like the more narrow we make all of them, then like the more specific and more sensitive overall our analysis is going to be. Just like a little technical background. So UHPLC system, or in this case, HPLC system, so high performance liquid chromatography, typically consists here of solvent reservoirs. So here there's, for example, like 4 different solvents, which we can then mix here through like a low pressure gradient mixer to our desired composition, before we then with a high pressure pump here put them to like a high pressure, and then it goes to like here a damper and a valve where we can inject our sample, and then through like different like filters, and then actually comes the injector, and then it goes onto like the column and gets like eventually separated. So now in a classic HPLC system, then we have like the detector, and there's like different properties typically used. So the idea is that I separate my molecules here on this column and then detect some properties of those compounds, right? So classically for HPLC, this would be UV spectroscopy, where I basically like see like light absorption depends on like the specific extinction coefficient of like a molecule I'm detecting, and then I get like a signal response and I get these peaks. So other than UV vis, fluorescence is commonly used. It's very sensitive. So like for like some pharmaceutical analytic, for example, like in production processes, also this is widely applied. Then light scattering, which is like a little bit less sensitive, but has like the very nice property that it's more like compound independent. So whereas like UV, you for example need like pi systems that you get some type of like absorption, but obviously not every molecule has that. So for some molecules you might be blind, but light scattering is like more universal there. And then refraction is another thing people use. And then for us, most importantly, mass spectrometry is widely applied now as like a detector for HPLC, or if you do high-end mass spec, then maybe your HPLC is more like the sample introduction system, but I leave that up to you. Okay, so yeah, just to give you like an idea how this looks, this is a photo Raphael took, who might be in the audience, together with Paolo and myself. So this is our HPLC system we have in the lab. So here, basically like this plaque tower here in the middle is like a pump and an auto sampler and then a column oven, where we do the separation of like the molecules by like reverse phase HPLC typically. And then you can see there's like this capillaries connecting like the two, and then going here to like this like little box here with like all the wires. This is our ESI interface, and then we have like the Q-exactive mass spectrometer at the end. All right, so then just to give you an idea how the data looks like. So here we have like a classic nice separation of a sample that may also contain some polymers. And you can see here on this one axis, we have like the retention time. And then on the second one, we have the mass over charge, so that the mass, our mass spec measures. And then like to the top, this is like intensity, right? So like it's a really like a 3D plot basically. And then, you can basically see it like from either side and look at like the TIC. So this would be the total ion current, where like basically the intensity from all ions would be summed up, or you could look at it from the top. So there's like different visualizations, and I'm gonna briefly highlight some at the end of the seminar today. But importantly is that this is like really like a high resolving analytical technique, right? Because you first have this chromatography dimension, and then you have like the mass dimension, and depending on the resolution of your machine, like at every given retention time, you can potentially detect like hundreds of different molecules. And then over like a, I don't know, 15 minutes gradient, of course, there can be like really a lot of compounds coming down. So I think for non-targeted metabolomics, this is probably like the most detailed information we can get, unless we would add now a fourth dimension such as ion mobility. But that's maybe will become more important in the future. But for now, I think this is already really like a nice detailed view of like the complexity, right? And we can detect and potentially identify like many compounds by their mass, as well as like retention time here. But now if we work with unknown compounds and mixtures, and ideally new natural products you will find from your I don't know, isolates or heterologous expression systems, you want to also know what those molecules are, right? And now you can maybe calculate already like a molecular formula from like the very accurate mass you would measure from with like the high resolution instruments we have available. But that's of course still can be like a lot of like different molecules or isomers that all share like the same molecular formula. So there, like I want to now introduce you like the next thing, which I think we mentioned already before, and this is tandem mass spectrometry. So now imagine like at every like here retention time moment, we could like take like some specific like molecules, and then basically pre-isolate them in our mass spectrometer, right? So that we would isolate, let's say, only one of like those peaks at a given mass, and then fragment them with, for example, collision-induced dissociation. So we let them collide against like a neutral collision gas, and then like terminally activate them till they basically break apart, right? And then we can do a second mass spectrometry step where we now take like all these fractions and then all these fragments, and then separate them again, and then get like a mass spectrum of those fragments from a particular molecule. And this is what basically tandem mass spectrometry does in a nutshell. And that is very cool because like depending on like the technique I use, those fragments kind of like like happening depending on the structure of the molecule. So here I just made this example up, but if we would take like domoic acid and we would have a technique that here breaks nicely like the CC bonds. Then eventually we could basically explain the structure of this molecule by the fragments we observe. Or more efficiently, if we have like a large library of like fragment spectra from MS-MS, we can search our experimental spectra against this library and annotate, basically like the identity. So if we have that available, and if we could do that, that would be, for example, like a level 2 identification. And we could be already like pretty sure that this is like likely our molecule candidate there. If we don't have like that available, we can use MS-MS to also de novo propose like the structure, especially for like peptides. This has been done or is still done like very like nicely, because peptides.
Du, ich habe nochmal, geht's gerade oder bist du auch bei diesem Seminar dabei?
Mute.
Dann mache ich ganz kurz, ich wollte nur kurz fragen, weißt
okay, so yeah, we can basically like build up like sequences from peptides by like de novo sequencing, and this works very nicely because peptides typically fragment with collision-induced dissociation at like the peptide bond. And yeah, it's very well understood how that behavior is. For like small molecules and metabolites, sometimes it's a little bit more complicated, and establishing a de novo structure is actually really hard. Anyway, so now I want to like show you like different ways how to do tandem mass spectrometry, and then at the end, so what I just showed you, the product ion scan, we want to also like come back to that. But before we do so, there's different ways how to acquire tandem mass spectrometry data, and this is really important for the type of experiment you do. So while like the product ion scan, where we basically look for like fragments from a particular precursor, are typically used for identification, we can also use tandem mass spectrometry where we already have some structural information or some information about a compound and search for similar compounds. And one very classic way to do so is the precursor ion scan. And you have to basically think about it in that way that you have like 2 mass spectrometers in a tandem mass spec experiment, right? And then in the middle, you have some type of like collision cell or other electron-based activation where you fragment those molecules. And now in a precursor ion scan, if you would basically set the MS2 mass spectra to only look for a particular mass, but you would scan at the same time with like the MS1 thing, then you could basically determine molecules that result in a certain fragment and then obtain their molecular weight or their mass, right? And this is very useful when you, for example, know, oh, I do like a certain derivatization and this results in like the addition of this like group, and that results in a specific fragment. Or if you look for like natural products and you know from genome mining, oh, there's like this N-terminal amino acids and it must be in there, right? And now I want to like look at all molecules in my sample that basically would result in a specific fragment I would expect for this amino acid to cause. And yeah, that way you can like screen quickly for like potential molecules that fit your criteria, and then eventually further make experiments with them to like identify what they are. This type of experiment is typically used in here scanning type triple quadrupole instruments. So it does not work with like a QTOF, for example. So you need to have like the capability like to scan through, well, actually it does work with a QTOF, sorry, but yeah, you need to basically have like the capability to fast scan through like your MS1 mass spec in this setup. Okay, then also with a triple quad, which is I think typically used for this type of experiment, you can use multi-reaction monitoring. So now you basically use both mass specs you have, and in this case could be like quadrupoles, for yeah, like not scanning, but to set them at particular mass ranges. So, and that has like now the advantage that you basically look only for something very specific, right? So if you would set your mass spec 1 for like 300, and then you know my molecule has these mass after fragmentation, or like the fragments have these mass, then yeah, you kind of like have like 2 steps of like criteria that need to be fulfilled in order for a molecule to cause like a signal here. And yeah, basically this provides you like a very high selectivity. So you're very specific, or specificity, you're very specific about the compounds you detect. And this also results in a very, very good signal to noise ratio. Probably like the best signal to noise you can typically get for like a mass spec analysis. This is why multi-reaction monitoring is kind of like the go-to experiment if you want to do quantitative analysis with your mass spec. So you look for, I don't know, like a certain vitamin in your samples, and then you know already what you're looking for. So then like LC triple quad would be basically like the go-to technique. That's why people, yeah, use this typically like in targeted metabolomics. So here in Hannes' lab, they have, for example, a triple quad, and then they have MRM methods for like a certain set of like metabolites that they're looking for. And then, yeah, with like external or internal calibration, they can get like calibration curves and accurately get absolute quant information for such things. Yeah, here again is like the animation for it. So as I said, like your mass spec 1 and your mass spec 2 are both set to like a fixed MZ value, and hence only molecules that will first have a certain mass, but then also produce a certain fragment ion will be basically making their way through and be detected. Okay, and yeah, just to give you like a little example how such an MRM chromatogram would look. So here we have like a crude extract, and we're looking basically like at this one molecule, and there is here like a single ion monitoring experiment on like the upper panel, where you can see already, well, there's actually like a lot of molecules that may have like the same mass, but now, and yeah, hence result in like this, what I would call not so nice peak, or like multiple overlapping peaks. And then on the bottom panel here, you see like this MRM analysis from like the same extract. And now if we add like the second condition in our MRM experiment, so like it needs to have this fragment with a certain mass, then yeah, we get like a nice peak here and a way better signal to noise, and also better dynamic range typically. So yeah, MRM in a triple quad is the MS experiment for quantitative question. And then yeah, now this one only works with a indeed triple quad neutral loss scan. This is kind of like a little bit like a exotic thing, but some people also use this. And this is when you, for example, know that like a certain molecule you're looking for, or class of molecule, have like different neutral losses, such as like they lose water, or like they lose CO2 in a certain fragmentation step, or it could also be like a terminal amino acid or something like that. And the idea here is that I scan through the mass range with both my MS1 and my MS2 at the same time. Now, the only difference is that I let them scan in a certain offset. And that offset is basically the mass of the neutral loss I expect. So here in the animation, yeah, you can basically see only things that go through that produce like a certain neutral loss. So in this case, it's water, right? Would then make the second step, because basically both mass specs are in sync with this offset, and yeah, like only let through stuff that basically produces like this different like neutral loss. So yeah, this is more like an exotic application, as I said, because that's, you need a triple quad to do that, but it can be quite informative. And yeah, maybe now a little spoiler for future seminars where probably Ming or somebody is going to talk about the mass spec query language. You can also mimic such an experiment with DDA product ion scan data in silico. So that's one of like, I think, the really cool applications of like advanced like bioinformatics analysis of mass spec data, where even if you only have like high-res DDA, MS data, you could look for things like that, which you would normally traditionally do in a neutral mass scan experiment. Okay, so yeah, I think these are like the three not so important scan modes. Probably MRM is the most important one for those, because this is, as I said, the go-to thing for targeted analysis. But yeah, now last but not least, the product ion scan, which I already like highlighted a little bit, was like the animation at the beginning. This is the yeah, I think key yeah, scan strategy for non-targeted metabolomics and for molecular networking. So that's why, okay, if the other three sounded confusing, this one here is really important, and you should probably like pay attention now extra closely. So in product ion scan, what we basically do is we set our MS1 to a fixed mass. We only let through like the green balls, right? And then we fragment them, and then we scan with our MS2, and then get like this product ion spectra. Some people also call this like daughter ion scan, but I would encourage you to use product ion. So this is by the yeah, like newest convention, the typical term to find this or to like call this type of experiment. So, and yeah, when you look at it, for example, like here we have rapamycin, like a famous natural product. If we would look here at this MS1 scan, so this is just a full scan of like the intact mass of these molecules, we would see, yeah, there's like 2 peaks here with like nice isotopes of like the, yeah, like here ammonia adduct of rapamycin. And then in a product ion scan, we would now do an isolation here, for example, of this mass 821, and then fragment this, right? And then we get the MS from it, a product ion scan, and this would be here, the different product ions. And yeah, as I said, so this can be used for spectrum library matching or for de novo compound annotation. And yeah, depending on your class, that sometimes works very well. So, and again, here in the animation, we separate molecules on the column, then isolate a particular species of ions in the quadrupole, fragment them in the HCD cell, and then get like this readout of like the product ions in the high resolution Orbitrap. I'm just gonna repeat it really quick. So here it's like the red square this time, we isolate and we fragment, and then here this exemplary 3 fragment ions we will then get as our MS spectrum. Okay. So now probably one valid question you might have is, how do you know in a non-targeted analysis to what masses you need to set your quadrupole before your analysis? And I think this is, for me, when I first learned about this, this was a kind of like a key moment, and I thought, oh yeah, cool, that makes a lot of sense, because what the mass spec is basically operated in is a somewhat like smart way, which we call data dependent acquisition. So DDA, this is a really important term you should probably like write down or yeah, like remember if you want to do non-targeted LC-MS based metabolomics in the future. And what DDA basically does is that it switches the acquisition mode of the mass spec between full scans, where we don't fragment and just get like an information of like all molecules that elute at a certain time, to MS scans. And then what it will use these MS1 scans for is kind of like a survey scan, where it actually checks, okay, what are like the signals that elute at a given time? And then in the consecutive MS scans, it picks the top masses that are present at the previous survey scan, and then submits them for MS. And it, yeah, basically runs through a kind of like circle, right? So like it's a rolling iterative process where we do this MS1 scans, and then depending on those information, the machine automatically picks masses which are submitted to MS-MS. So this is really like non-targeted, right? Because it like picks up what is present at a given time. And now there's like a couple of like different settings, which I think we're going to talk more about like next time. But basically you can like then put like different conditions about charge state, about repetition, right? So like once one ion is fragmented, then you don't want to like do it over and over again because you already have an MS-MS, so you can put this on a so-called exclusion list for a certain time. And then, yeah, like this ideally cycle rolls through your chromatogram, and yeah, ideally you get like a high coverage of all molecules that are eluting. Obviously, like the more complex that thing is, that sample is, the less likely it is that you will cover all. And then one very important thing, obviously, the faster your mass spec scans, the deeper you can go into like the coverage of your samples. And this has been something which I'm like absolutely fascinated about. And this is the basically gain and speed of like different mass specs over the last 10 years or so. So yeah, here, while in this animation it happens really slow, so you can actually follow it. Like when you look here at the bottom, this is just like a GIF of a by now older generation Orbitrap, and like this data dependent acquisition happens really fast. So it's like in the, I don't know, second range per duty cycle, right? So like one of these cycles takes like a second or so. So you want to ensure that it's not too long in order to maintain enough data points for good chromatography. But then, yeah, like you get like top 5 or top 10 or top 20 MS-MS spectra within each duty cycle. Right? And yeah, this is really like directly coupled to the speed of your mass spec. So now with like the latest Orbitraps, for example, you probably can scan at like 40 hertz, which means you would get up to like 40 spectra per second. Then you can like now do the math over like a, I don't know, 10-minute gradients. This is a couple of thousand MS-MS spectra, right? So this is really a lot of like information. And I think this is also the reason why with like manual data analysis, we can't really do much there anymore, unless we know already what we're looking for. And yeah, just to give you like some examples how this looks. So this was a molecule I worked a lot with during my PhD. This is albicidine. It's a non-ribosomal peptide, and it fragments really nicely here at this amide bonds, as I mentioned. And yeah, it's also like a cool antibiotic and has some nice properties. But what was probably most interesting for me in this context was that I could annotate very nicely here, like these different fragments. So we get this B and Y ion fragment series. And then by comparing this to other spectra from like the same data set, which I acquired in data-dependent acquisition mode, I could actually find a couple of other derivatives that had very similar fragmentation patterns, and but different precursor masses, right? And now here, you can maybe see it here on the N-terminus. There's here, for example, like this carbamylation as a modification. So this here would be a new derivative. Or then here, we have even another one that in addition to this carbamylation has here a methoxy group and an asparagine instead of like the cyanoalanine here at the central amino acid. So yeah, here I think MS-MS enabled us really quickly to actually propose those structures, because we knew already albicidine from NMR studies. And then, yeah, we basically got like now 2 additional candidates, which was very exciting. And this example of like comparing the spectral similarity here between different like experimental spectra that are acquired in the non-targeted MS-MS experiment, I think is also like the perfect example of what's happening in molecular networking. So now, instead of like, annotating this manually in molecular networking, I would just like take all experimental MS-MS spectra from a given data set and then compare them to each other and then organize them by their spectral similarity, right? So like if they basically have like similar patterns, which we can define through like a cosine metric, for example, then I can basically like connect them here as such nodes, and then basically structure that experimental space of MS-MS spectra of my data set. And if you have thousands of MS-MS spectra, certainly do not want to like go through manual anymore. So I think for me, this has been really like a game changer, and I was like super stoked when I first saw this like in a paper or poster. It's been cool work, and I think was part of the reason why I then really wanted to join the Dorestein lab in San Diego to learn more about this. So now, like the way how you deal with this would be, you construct this as a molecular network, and then you can basically compare some of like, or all of them against the spectral library, and then eventually you can identify a certain molecule and then propagate the annotation to the surrounding nodes, right? So here, for example, the one with the green check mark, we would have a library annotation to an amino acid. So, and because there's a high spectral similarity between like node E and G, then we probably know, or like we probably can easily propose that there might be like an amino acid or something similar involved too, right? Or in my case, for the albicydins, besides like the few ones I already like annotated by hand, I did another like analysis with molecular networking, where now in an unbiased, reproducible fashion, the algorithm actually told me which spectra are similar here, and that way, we could then actually retrieve like this entire molecular family here, where we identified actually like a bunch of other derivatives we did not know about before. So from my perspective, this is a really powerful analysis tool. And in addition to other like bioinformatic concepts for mass spec data analysis, I think is one of like the key elements in our data analysis in the lab. And I think for like the seminar, learning how to make molecular networks and how to deal with this data and visualize it, this will be one of the main learning objectives. All right, but now enough of like the theory for today, and for the next 15 minutes, I actually want to do it's like some hands-on examples with you, where we're just gonna dive a little bit into LC-MS data, and then also take a brief look at the molecular network and try to just navigate a little bit in that space. And as an example data, I'm gonna use here non-targeted MS data from E. coli Nissl, which I think is a very interesting bug in our guts, which also is used as a probiotic. And there's a lot of work done, and it makes some really cool natural products. For example, some siderophores in which we were like particularly interested, and I don't want to spoil too much, but like this basically was like part of like a new tool we developed, which is native metabolomics, and I don't know, it's I think a cool example molecule which we described here in this paper. Anyway, now most important for you is this URL here, which I actually can also try and paste quickly in the chat, so you don't have to type it. Find the chat. All right, and you just can click on this, and then I actually just gonna do that now too in my browser, and then you should get to wait, what's this? You should get to this Google Doc here. Does that work for everybody? Okay, I see some people joining, so looks like it's working. Great, and basically here I provided you two links, which first contains already a ready made molecular network, and then another link which brings you to the GMPS dashboard. And I actually had something here. Oh yeah, before we go into that, I want to point out one person who has been like absolutely critical to all this, and this is Ming Wang. He's still a postdoc in Peter's lab, but he's basically like the architect behind like all like the software here. And yeah, if you see Ming at the conference, maybe buy him a beer if you find those tools useful. So I think that's really like key to point out. So thank you, Ming, for building this. All right, but let's go back to our Google Doc. So yeah, just like click here on this link, and then you should get to the GMPS homepage and directly here to this molecular networking visualizer. And if you click somewhere here in the network, then yeah, you should see that there is a lot of gray nodes, and then there is also a blue node. Okay, and now, as you could probably see here from our objectives for our hands-on today, we just want to find now Yersinia bactin derivatives, and then compare a wild type to a knockout strain in the second step. But yeah, now to find Yersinia bactin derivatives inside of that network is actually pretty easy because yeah, it's already the Yersinia bactin network I selected here for you. And through like this different node label options here on the left, you can toggle between annotations of those nodes, and then, for example, go to parent mass, which should be precursor mass. I don't know why this is still called parent mass here. And then you could look now for the mass of Yersinia bactin, or because there's also this library ID button, you can click this library ID button, and then it basically labels all the nodes that have been matched successfully against the spectrum from like the GMPS library. And then we would see, okay, now cool, here there's Yersinia bactin, or at least one of the isomers of it. And now, yeah, you can basically click on this, and then, yeah, then it should start displaying here MS spectrum on the right. There's like this little magic stick button, so you could also like annotate now the masses, and then yeah, you could start comparing this to the MS spectra of like the surrounding nodes here. And again, yeah, those connections are based on MS similarities, so everything that's connected here should have a similar MS spectrum, right? And if we label this again, it's like parent mass, excuse me, precursor mass, then we would see, oh, there's a couple of other molecules that have similar MS spectra that are connected, right? Because they have similar MS spectra. If you want to visualize this in comparison, you can right-click on one of those. Okay, let's, for example, choose this one. And then also here with the magic stick, they should be displayed in the lower panel, and we can actually compare then the masses. And you would see, oh, actually many of these masses are similar, right? So like the MS spectrum is very similar, but the precursor masses have a difference here, in this case of 14, which you can also directly label inside of that molecular network. When you click here on the delta MZ edge label, it will like display this here, right? And I just scrolled in with my mouse, so yeah, feel free to move around a little bit. And then yeah, basically I could now propagate that there is a certain derivative that has a mass offset of 14 MZ. And I don't know, natural product chemists here, somebody wants to make like a quick suggestion what this mass difference could be.
Methanol.
Sorry, can you say it again?
Methanol, a methyl group.
Methyl,
right?
yeah.
Yeah, methyl group.
So not, yeah, CH2, right? That would be 14. And then what else do we have? Some more suggestions for the other masses. I'm sure Tam knows one.
21 is natrium, sodium.
Yeah, 21.98, I think that could be sodium. So that would be a different adduct then, right? Unless we have a weird metallo-organic compound. But yeah, sodium we typically observe as different like adducts. More suggestions?
Maybe the mass difference of 2 is a double bond that formed or got destroyed. So
Yeah.
in either direction.
So it's H2, right? Yeah, could be. So yeah, I think we already have some ideas. Yeah, typically, I don't know if there's some other common things. Yeah, I don't know about the 16, but some delta masses we often observe is like oxygen, so 15.99. Then like 2 methyl groups, or like ethyl, so that would be 28. Then acetyl. So there's certain like modifications you would observe quite regular if you go through like a couple of like different networks. And then obviously, yeah, the structure of your Bactin is known. And yeah, you can basically then draw it and come up with like possible modifications that could yield in these mass differences. So yeah, I hope that this could be already pretty useful if you have a natural product now and you want to like sketch out a little bit like the chemical space around it. So I find like those molecular networks come in very handy. Now, what we can also do from here, because we structured already now this information, is we can actually go back to the raw data from that. And there is, yeah, a development I'm like particularly excited about, and that is the GMPS dashboard. Because in addition to like, yeah, just looking at like this condensed form of information in these molecular networks, we can actually go back to the yeah, like original HPLC-MS data. And to do so, I can here click on this cluster spectra link, or here this cluster spectra link. And then what it actually should do is it should open this new window where now all MS spectra that were identical and basically combined in this node are listed. Because yeah, obviously if you run a sample multiple times, you know, then you would eventually like create a lot of MS spectra from the same compound, and hence yeah, would create a lot of redundancy. That's why here in this classic molecular networking, they're like collapsed to a node. But yeah, basically by clicking on this cluster spectra, you can see all spectra that contributed to that cluster. And if you would here click on this view spectra button, you will see that they all look very similar, if not identical, because they're clustered. But then the cool thing is that now there is this link here, view LC-MS chromatogram. And when you click on this, it should bring you directly to the GMPS dashboard with particularly here this sample under this file name, and load this already in this visualization tool. And now, yeah, I think for the next 5 minutes, I want you to yeah, play around basically a little bit with that, and yeah, go through. So it eventually takes a couple of seconds to load, but now, yeah, because we're like using it all at the same time, maybe normally it should be a little faster. Anyway, so now it loaded here on my end, and what you can see is kind of like the full LC-MS file. And now one of the visualizations here on the left would be this 2D heat map. And I think this is already a really nice view because it gives you an overview of your LC-MS chromatogram. And now if you wonder what these blue things are, so these blue things are basically markers that indicate every MS event. And if you want to remove them, you can just go here and say show MS2 marker and turn this off. Then it should now, yeah, only show our MS1 data. And then, yeah, basically what I showed you in this 3D plot, we kind of like see here just in a 2D version with this heat map, right? And like intensity is indicated through like this color gradient. And now you see, yeah, over time, there's really like hundreds of different compounds eluding here and creating here like different peaks in our mass spectra, right? And then if I would scroll farther down, this is now the TIC, the total ion chromatogram or total ion current, where all this MS information is basically condensed in just one signal. So this is how a normal chromatogram would look like, right? But just now think about that behind each of those peaks here, there is actually all that information which you can see on this top view in the y-axis. Okay, and now, yeah, again, if I turn on here to show MS2 marker, now I see all the DDA MS scans over the course of like this experiment. And as I said, there are a couple of thousand, so this is a lot of information, right? But yeah, now if we already have this condensed in the molecular networks and we want to like go and check something in detail here, we can do so. Right? And one way would be to create an XIC. XIC stands for extracted ion chromatogram, where I basically now extract the mass trace out of this data by typing in here the mass I'm looking for, and this is the mass of Yersinia bactin. That should be already pre-populated because we came here from like the network. And then here under it, I can like define tolerances, here either in absolute or in relative. So we use high resolution mass spec data, so we probably want to use ppm. 10 ppm would be like a default. I can change this here to ppm. And then on the bottom here, it should now basically plot the XICs for Yersinia bactin. And now here my MS2 events are indicated as these red markers instead of blue. And when I click on one of them, I can see here the MS spectra of Yersinia bactin, or of this mass of Yersinia bactin. And now, very interestingly, if I click on the other one here from the other chromatographic peak, let's see, then 295, 199, let's see this again, 295 also here, and 190, right? So, oops, need to hit it, yeah. So they have very similar MS spectra, those two peaks, right? Now, the interesting question is, why are there two chromatographic peaks, but we only had one node in our molecular network with 482, right? So that's the mass I added here, and yeah. So, and they both have like very similar MS spectra, and that's already the answer to my question, because actually they have the same MS spectra. So what happened here in the network is that they were all combined. And that's, I think, a perfect example why it is important to also look at the chromatograms. Because here, and maybe somebody can give a suggestion or an idea what this could be, but apparently there's more than one form of like Yersinia bactin. So any idea why we could have two peaks there?
Isomer.
Mm-hmm. Yeah, and it's not kind of like isomer in sense of like a certain like group is like elsewhere, because then that typically would result in different MS fragmentation. But in particular, the example of Yersinia bactin, we have diastereomers. So like, yeah, that basically have like two chiral centers, and yeah, they're not really like distinguishable by MS. So this is one of the, I think, yeah, like things we cannot do yet with MS to determine like stereochemistry. But here with chromatography, those two diastereomers are like very nicely separated. And yeah, we confirmed this downstream, and I know this, and we also have an idea how it happens. But yeah, so this is an important example why actually combining this chromatographic information with MS information is really powerful. And this is what we do in feature-based molecular networking, where we actually first extract chromatograms from like different molecules and then add MS as a yeah, like qualitative information to them. And yeah, in the course of the seminar, we're gonna introduce like different tools how to do this systematically and use feature-based molecular networking. Okay, we're close at 12. So now I just want to show you one last thing, and that is here in the second link in the document I shared with you. If you click on that, it should now open a new visualization of the dashboard, also for Yersinia Bactin. But now here in the file selection region, you will see that here I loaded in multiple samples. And now you can see actually from their names, some of them are called N and the other ones are called P. And that's important because one is the wild type and the other one is the Yersinia Bactin gene cluster deletion mutant. So I think here one of the NRPS genes are knocked out, and this theoretically should not produce Yersinia Bactin. So now, very nicely within the dashboard, if we load multiple files, we can do already like some peak extraction and get actually peak areas. Well, first we can compare them, of course. So here we see, yeah, there's those peaks, and then here in our knockout, there's none. And then if we scroll through to the bottom, we can directly see this visualized here, this box plot. And yeah, we had still doubts that this molecule was Yersinia Bactin. The latest now was the knockout mutant. We could like nicely confirm, well, that this is indeed a product of this particular gene cluster and very likely Yersinia Bactin. All right, I think with that, that's pretty much it for today. It's 12. I hope it was fun, especially the hands-on part. I still have time to stay on for a little bit. So if you have questions, we can still have like some discussion session now. If you want to head out, feel free to continue with your other stuff, of course. Yeah, thanks for listening.